Welcome to the deep dive. Today, we are really getting into the thick of it with a component that takes an incredible amount of stress, the aircraft propeller.
That's right. We're focusing on Chapter 7 from the AMT Powerplant curriculum.
And the mission, as always, is to pull out those absolutely critical nuggets of knowledge.
Yeah.
Stuff you really need to grasp, not just memorize, for when you're working on these systems.
Exactly. Because the propeller, well, it's where the engine's power meets the air. It takes that rotational force from the engine.
The brake horsepower BHP.
Right, the BHP. And it has to convert that efficiently, hopefully, into thrust horsepower, THP. That's the force that actually moves the aircraft forward.
It's a pretty amazing piece of engineering when you think about it. And the journey from those early, simple wooden props.
Yeah, like laminated tubulators.
Where the complex, multi-bladed metal and composite ones we see now, it's huge. But there's a fundamental limit, isn't there? A wall they hit.
There absolutely is. It's physics, basically. Propeller aircraft just can't really go much faster than about 400 miles per hour, give or take.
And why is that? What happens?
It's all about the blade tips. As the aircraft speeds up, the tips are moving even faster, right? Rotation plus forward speed.
Okay.
And eventually, those tips start approaching, or even exceeding, the speed of sound. Mach 0.8, Mach 0.9.
And that's bad. Very bad.
Very bad. You get shock waves forming on the blades. That's what we call excessive blade tip speed.
So efficiency plummets.
Plummets. Suddenly, a huge chunk of the engine's power is just making noise and shock waves instead of thrust. And the vibration, it becomes intense.
Leads to fluttering.
Exactly. Fluttering is this destructive oscillation that can literally tear a blade apart. It's the hard limit. That's why, for faster flight, we had to go to jets and turbofans. The prop just couldn't keep up.
Okay, so foundational stuff. Let's get the terminology straight. If you're looking at a propeller blade, thinking of it like a rotating wing, what are the key parts an AMT needs to know instantly?
All right, nomenclature 101. You've got the edge cutting the air. That's the leading edge.
Got it.
The opposite edge is the trailing edge. Then, obviously, the outer end is the blade tip.
And the central part.
That's the hub, or sometimes called the boss. Super strong. It mounts the whole thing to the engine shaft.
Okay, and the blade surface.
The side facing forward, generally flatter, is the blade face. The curved side, the airfoil side, creating the low pressure, that's the blade back.
Right, cambered side.
Yeah. Then, near the hub, it gets thick and rounded for strength. That's the blade shank.
Where the stresses are highest.
Exactly. And the very end piece that actually fits into the hub mechanism is the blade butt or the root.
And for inspection and analysis, these blades are looked at in sections, right?
Yes, definitely. You don't just treat it as one piece. Think of it as many small airfoils stacked together. We measure these sections using station numbers.
Station numbers? Like distance from the center?
Precisely. Usually in 6-inch steps out from the hub center. It lets you pinpoint where damage is or where adjustments are made. Very important for maintenance limits.
Okay, now the big one. The terms people always mix up. Pitch versus blade angle. Let's nail this down.
Yeah, this trips people up. They seem interchangeable, but they're not quite the same. Blade angle is simple. It's a physical angle.
Measured how?
It's the angle in degrees between the chord line of a blade section, that imaginary line from leading to trailing edge, and the plane the whole propeller is spinning in.
Okay, a direct measurement. That's what the system controls.
That's exactly what the constant speed governor is physically changing. Now, pitch. Pitch relates to movement. How far forward the prop wants to go.
Right, like the thread on a screw.
Kind of, yeah. But we have two types here. Geometric pitch is the theoretical distance. Imagine screwing it into something solid, no give. How far would it move in one turn?
The ideal distance.
The ideal. But air isn't solid, it slips. So effective pitch is the actual distance the aircraft really moves forward in one revolution.
And the difference between those two, that's slip.
That's propeller slip. And slip is why propellers aren't 100% efficient. You always lose some ground compared to the geometric ideal.
What kind of efficiency numbers are we talking?
Oh, it varies. Maybe 50% efficiency when you're slow, like on takeoff roll. But in cruise, a good constant speed prop might hit, say, 85%, maybe even 87%. Minimizing slip is key.
Which brings us to angle of attack, the AOA. The blade works partly by pushing air back, but also like a wing, right?
Yeah.
Low pressure on the front.
Exactly. That airfoil shape is crucial. And just like a wing, it works best at a specific angle to the oncoming air. For props, the AOA needs to be small and positive.
How small?
Really small. Typically only between 2 degrees and 4 degrees positive. Too high, it stalls, thrust drops. Too low or negative, it just slices air. No useful work.
So the whole point of a constant speed system is just to maintain that tiny 2 to 4 degree AOA.
That's its entire job, regardless of airspeed, engine power. Keep that AOA in the sweet spot for maximum efficiency.
Okay, let's talk forces, because understanding the physics here explains why maintenance is so critical. What's the number one force acting on these blades?
Oh, easily. Centrifugal force, no question. It's trying to rip the blade straight out of the hub, radially outward.
It's significant.
Significant is an understatement. At high RPM on a larger prop, you could be looking at 25 tons, 50,000 pounds.
Per blade.
Per blade, trying to pull it out. That dictates everything about the hub design, the blade shank reinforcement, the materials. Massive safety factors are built in.
Which means even a tiny bit of damage.
Can be catastrophic.
Yeah.
Because that force is immense. Blade weight itself becomes a huge design factor because weight equals more centrifugal force.
Okay, besides being pulled outwards, what other forces are trying to bend the blades?
Right, there are bending forces too. First, you have torque bending force. That's the air resisting the rotation. It tries to bend the blades backward, opposite the direction they're turning.
Makes sense. Air resistance.
Yep. Then there's thrust bending force. The propeller is generating massive thrust forward, pulling the plane. That load naturally tries to bend the blades slightly forward.
Okay, outward pulling, backward bending from torque, forward bending from thrust. Now, the twisting forces. These are actually used by the system, right?
They are. This is where it gets clever. There are two natural moments trying to twist the blade around its own axis, changing its pitch. First is the centrifugal twisting force, or CTF.
And that comes from?
It happens because the blade's center of mass isn't perfectly aligned with the pitch change axis. So as it spins, centrifugal force creates a twisting moment. And crucially, CTF always tries to twist the blade toward a low angle, a low pitch.
Okay, CTF wants low pitch. What's the opposing force?
That's the aerodynamic twisting force, or ATF. This comes from the way air pressure is distributed over the blade's airfoil shape. It naturally tries to twist the blade towards a high angle, a high pitch.
So CTF low, ATF high. Which one usually wins? Or is stronger?
Generally, the centrifugal twisting force, CTF, is designed to be the dominant one. The blade's natural tendency, if left alone, is often to go to low pitch because of CTF.
How does that play into pitch control then?
Well, in many systems, especially simpler ones, governor oil pressure is used to push the blades towards low pitch, fighting against ATF and maybe springs. In single-acting feathering systems, it's often the reverse.
Oh, so?
In those, you might have strong springs or even air pressure designed to drive the blade towards high pitch or feather, overpowering CTF. Then, governor oil pressure is used to force it back down to low pitch, fighting those springs. It depends on the design philosophy.
It's an incredible balancing act. Hydraulics, aerodynamics, massive physical forces.
Absolutely. And it hammers home why stress is such a big deal. Stress increases like crazy with RPM, and it's most concentrated right near the hub, at the shank.
So that nick or scratch we mentioned
Becomes a stress concentrator. A tiny flaw focuses all those immense forces onto one microscopic point. That's where fatigue cracks start.
And that leads to failure. Or flutter.
Right. If the crack grows, you could lose a blade catastrophically. Or the changing stress patterns can cause that rapid twisting oscillation fluttering, which just destroys the blade and shakes the engine violently. Maintenance isn't just routine, it's preventing disaster.
Let's categorize the props then, starting with the simplest. The fixed pitch propeller.
Okay. Fixed pitch, name says it all. The blade angle is set at the factory, usually just one piece of metal or laminated wood.
Birch was common for wood, right? Layers glued up.
Yeah, birch was popular. Now, more often it's a single aluminum alloy, casting or forging. They're simple, relatively cheap, reliable. That's why you see them on, basic trainers and light aircraft.
But the big downside is performance compromise.
Huge compromise. You have to pick one blade angle. Is it optimized for takeoff climb? Then it's inefficient in cruise. Optimized for cruise, your takeoff run suffers. You can't have both.
We should also mention test club propellers. Not for flying.
Right. Strictly for ground use. They're often chunky, multi-bladed things, maybe wood or composite, designed specifically for breaking in new or overhauled engines.
Why a special prop for that?
2 reasons. 1, they put the right heavy load on the engine to help seat the piston rings properly during break-in. 2, they move a lot of air for cooling when the engine's just sitting there on a test stand, not moving.
Okay, moving beyond fixed. What were the steps towards adjustable pitch?
Well, there was the ground adjustable type first. You could change the pitch, but only on the ground with tools. Not very practical.
Didn't really catch on widely.
No. The next big step was the controllable pitch propeller. This was a game changer. The pilot could actually change the pitch in flight.
Usually just two positions, like takeoff and cruise.
Often, yeah. Maybe a low pitch for takeoff, high pitch for cruise. But, and this is key, it was manual. The pilot had to decide when to change it and actively make the adjustment. If speed changed, the pilot had to tweak it again, not automatic.
Which leads us to the modern standard, the constant speed propeller.
This is the one. The system uses an engine-driven governor, a very smart hydraulic device, to automatically adjust the blade angle, the pitch, continuously.
And its goal isn't a specific pitch, but a specific RPM.
Exactly. The pilot sets a desired engine RPM using a lever in the cockpit. The governor's only job is to hold that RPM steady by constantly adjusting the blade pitch, no matter what the plane is doing or how much power the engine is making.
So it maximizes efficiency across the board.
Pretty much. It keeps the engine in its happy place, RPM-wise, giving you the best thrust and fuel economy, whether you're taking off, climbing, or cruising. Frees up the pilot, too.
Let's walk through a flight. Takeoff. What does the system do?
Okay, takeoff. Pilot pushes the prop lever full forward, selecting the highest allowed RPM, say 2,700 RPM.
And the governor responds by?
Driving the blades to a low pitch, a small angle. Think of it like being in first gear.
By low pitch.
Because at low airspeed, a low pitch takes a smaller bite of air. This puts a light load on the engine, allowing it to spin up quickly to that high 2,700 RPM and convert lots of fuel into maximum thrust for takeoff. It also keeps that critical AOA small.
Okay, now the aircraft climbs out, gains speed, heading for cruise.
Right. As airspeed increases, the air hits the blades faster. If the pitch stayed low, the engine would start to overspeed, go past the 2,700 RPM target.
Like coasting downhill in first gear.
Exactly. So the governor senses that tendency to overspeed. It automatically increases the blade angle to a higher pitch.
Shifting to a higher gear.
Perfect analogy. The higher pitch takes a bigger bite of air per revolution. This puts a heavier load on the engine, which naturally slows it back down to the RPM the pilot selected for a cruise, maybe 2,400 RPM.
So slower engine speed, less fuel burn, but still efficient thrust because the AOA is maintained relative to the faster airspeed.
That's the magic of it. Load matching to maintain RPM and optimal AOA.
The governor is obviously central to all this, the brain, you said, and it does two things.
Two main jobs, yeah. It's mounted on the engine, geared to the crankshaft. First, it's an incredibly precise RPM sensor. Second, it's a high-pressure oil pump.
High pressure? How high?
It takes regular engine oil and boosts the pressure way up, typically around 300 psi, sometimes more. It needs that force to move the pitch change mechanism in the prop hub against those strong internal forces like CTF and springs.
Okay, inside the governor, what are the key parts making the decisions? The control trio.
Right. At the heart of a typical single-acting governor, you've got three main players. First, the flyweights. These are L-shaped weights that spin around, driven by the engine. Centrifugal force makes them want to fly outward.
Faster spin, more outward force.
Exactly. Second, opposing them is the speeder spring. This is a coil spring, and its compression, its tension, is set directly by the pilot's prop control lever in the cockpit. More tension means a higher target RPM.
So flyweights versus speeder spring. What's the third part?
The pilot valve. It's basically a spool valve, moved up and down by the balance point between the flyweights pushing up and the speeder spring pushing down. This valve is what directs that 300 psi oil.
Okay, let's use those parts to explain the three operating conditions. First, everything stable, on speed.
On speed, perfect balance. The outward force from the spinning flyweights exactly equals the downward force from the speeder spring.
So the pilot valve.
Stays right in the middle. It's centered. And when it's centered, it blocks both the path for high-pressure oil to the propeller and the path for oil to drain from the propeller.
Oil is trapped.
Oil is trapped in the prop hub. The pitch doesn't change. The RPM stays exactly where the pilot set it. Equilibrium.
Now, something changes. Maybe the plane pitches up, airspeed drops slightly, the engine load increases, RPM starts to fall. Under speed.
Under speed condition. RPM drops, so the flyweight spins slower, less centrifugal force.
Meaning the speeder spring wins.
The speeder spring overpowers the weaker flyweight force. It pushes the flyweights inward, which forces the pilot valve down.
And a downward pilot valve.
Opens the port. It directs that 300 psi governor oil pressure to the propeller hub piston.
And that oil pressure makes the blades do what?
It drives the blades towards a lower pitch. Remember, lower pitch means less load on the engine.
It takes the load off so the engine can speed back up to the target RPM.
Precisely. RPM increases, flyweight force builds back up, the pilot valve recenters, oil flow stops, and we're back on speed at the desired RPM.
Okay, the opposite scenario. Aircraft noses down, airspeed increases, windmilling effect, engine RPM starts to climb above the target.
Overspeed.
Overspeed. RPM goes up, flyweights spin faster, generating more centrifugal force.
Now the flyweights overpower the speeder spring.
They do. They fly further outward, lifting the pilot valve up.
And when the pilot valve goes up,
It opens a different path. It allows the oil that was trapped in the propeller piston to drain out and return back to the engine sump.
so the high pressure holding the pitch is gone. What takes over? Now, those internal prop forces we talked about, maybe aerodynamic twisting force, maybe internal springs or counterweights. Depending on the design, they immediately drive the blades towards a higher pitch.
Higher pitch, bigger bite of air, more load.
More load slows the engine down. RPM decreases back to the target speed. As it stabilizes, flyweight force reduces. The pilot valve centers itself again, trapping oil and locking the new higher pitch. Back on speed.
It's a constant dynamic adjustment. Pretty neat. Let's move into more advanced features, especially for multi-engine aircraft. Safety is paramount, so feathering propellers.
Absolutely vital on twins and turboprops. If an engine fails, you have a massive source of drag from that windmilling propeller. Feathering means rotating the blades edge onto the wind.
To almost 90 degrees.
Yeah, close to 90 degrees, parallel to the airflow. This stops the dead engine from spinning wildly, drastically reduces drag, and makes the aircraft controllable on the remaining engine. Huge safety feature.
How is that extreme pitch change usually achieved, especially on, say, light twins?
Often, it's a single acting system. This means oil pressure from the governor is only used for unfeathering or moving to low pitch.
So what moves it to feather?
Internal forces take over when oil pressure is removed. This could be a powerful feathering spring inside the hub, sometimes compressed air stored in the hub, or harnessing the centrifugal twisting moment of the blades themselves, all designed to drive the blades toward the high-pitch feather position when that governor oil pressure is dumped.
So losing oil pressure automatically feathers it, in many cases.
In many designs, yes. Or the pilot actively dumps the pressure via the feathering control.
You mentioned feathering latches or start locks earlier. Why are they so important? How do they work?
Critical safety device. Since the prop wants to go to feather when the engine stops and oil pressure bleeds off, these latches engage at shutdown. They're little centrifugal locks.
What do they lock?
They physically lock the blades in the low pitch position when RPM is very low or zero. If they didn't, the prop would feather on shutdown.
And trying to start the engine against a feathered prop would be bad?
Really bad. Massive load. Could cause a hot start, damage the starter, or worse. So the latches hold it in low pitch for starting. Then, as the engine starts and RPM comes up, usually above 600 to 800 RPM, centrifugal force acts on the latches themselves, pulling them out of the way, disengaging them.
So they automatically unlock once the engine is running.
Yep. Then the governor has full control.
Okay, engine failed, prop feathered. How do you get it out of feather if you want to try an air start?
Yeah.
Unfeathering.
You need to get oil pressure back into that prop piston to drive the blades away from 90 degrees. If the engine windmills fast enough upon restarting, the governor pump might do it.
But maybe not reliably.
Maybe not. So more common methods are needed. One is an accumulator. It's basically a small bottle storing oil under high pressure, usually from a nitrogen charge. Flipping the switch releases this stored pressure to push the blades out of feather quickly.
Or a separate pump.
Yes, some aircraft have an auxiliary electric unfeathering pump solely for this purpose, provides the pressure needed to get things moving again.
Okay, back on the ground. Reverse pitch propellers. Mostly turboprops.
Mostly turboprops, yeah, and some larger piston aircraft. Reverse pitch is exactly what it sounds like. The blade angle goes past the normal low pitch into negative angles.
So pushes air forward.
It generates thrust in the opposite direction of flight. It's used for aerodynamic braking after landing, helps slow the aircraft down quickly, saves a lot of wear on the wheel brakes. Very effective.
And with turboprops like the common PT6, control gets even more sophisticated. Talk about the alpha and beta ranges.
Right. This blends engine power and prop pitch control. Alpha range is the flight mode. Normal operations, takeoff to landing approach.
What's the priority in alpha range?
Constant engine speed. Usually the propeller governor works to maintain 100% of the rated propeller RPM, NP. The pilot adjusts the power lever, which controls fuel flow and thus engine torque, or turbine inlet temperature, TIT. The governor then automatically adjusts the blade pitch to absorb that torque and keep the RPM steady.
So prop pitch follows engine power to hold RPM.
Essentially, yes. Now, when the pilot pulls the power lever back past a certain point, often a gate called flight idle.
You enter the beta range. Ground only.
Strictly ground operations. Taxi, ground maneuvering, and reverse thrust. In beta, the governor's automatic RPM control is basically switched off.
So what controls the pitch?
The power lever itself, directly and mechanically. Moving the lever now directly changes the blade pitch angle. The pilot is manually selecting pitch for taxi speed or pulling it further back into the reverse range for braking.
And the PT6 specifically has another safety system, NTS.
Yes, negative torque sensing. Crucial protection for the engine gearbox. If, for some reason, the airflow starts driving the propeller, which in turn tries to drive the engine backward.
Like in a dive or sudden shutdown.
Right. That creates negative torque on the propeller shaft. The NTS system mechanically senses this backward force.
And what does it do?
It triggers a valve, a dedicated feather valve, that instantly dumps governor oil pressure from the prop. This allows the prop's internal feathering mechanism, usually strong springs in a PT6, to rapidly drive the blades towards the feather position, even if the pilot hasn't commanded it.
Preventing the prop from driving the engine into self-destruction.
Exactly. Protects the reduction gearbox and the whole engine from massive reverse loads.
Okay, let's shift to maintenance. This is core stuff for the AMT. Given those huge forces, inspection has to be top-notch. What's the everyday focus?
It starts with the visual. You're looking for obvious things. Oil leaks, grease spatters from seals, loose screws, any signs of damage. But you can't stop there.
Need to look closer.
Much closer. Use a magnifying glass, especially around the blade shank and where the blade enters the hub. These are high-stress zones. You're hunting for tiny nicks, scratches, corrosion pits, any flaw that could become a starting point for a crack. And something often overlooked but critical: checking tachometer accuracy. Why is that tied to prop maintenance?
Because if the tachometer in the cockpit is reading low, the pilot might think they're at the red line RPM, but they could actually be significantly over it.
Right. Consistently overspeeding the engine and prop, even by a little, puts immense cumulative stress on everything, especially the propeller hub and blades. It can lead directly to fatigue failure. So verifying TASH accuracy at every 100-hour or annual is mandatory.
What about a ground strike? Blade hits the runway, a taxi light, even seems minor.
Rule number 1, any prop strike or any sudden engine stoppage means mandatory action. Don't guess.
Which is?
Full disassembly and inspection of the propeller assembly, period. And often it requires engine inspection too, especially the crankshaft and gearbox, looking for internal shock damage or misalignment. The manufacturer's maintenance manual is the absolute authority here. External damage might look small, but internal stresses could have initiated serious hidden flaws.
Let's talk materials. Inspecting wood props. What are the gotchas?
With wood, you worry about the structure and moisture. Look for signs of the glue joints failing between the laminations. Check for warping, cracks, especially near the hub or under the metal tipping on the leading edge.
Metal tipping.
Yeah, thin metal sheath for erosion protection. Check that it's secure, no loose rivets. And crucially, find the tiny moisture drain holes in that tipping, usually near the tip.
Why are those holes important?
They have to be open. If they get plugged, moisture can condense inside the blade under the tipping. That leads to internal rot, throws off the balance. Big problems.
Okay. For metal blades, aluminum or steel, what's the main killer?
Fatigue cracks. And the absolute showstopper is a transverse crack one running across the blade, perpendicular to the leading edge. Any sign of that, the blade is scrap. No repairs allowed.
How do you find cracks that aren't obvious?
NDT, non-destructive testing. For aluminum blades, liquid penetrant inspection, LPI, often using fluorescent dye under UV light, is common. It wicks into surface cracks and makes them visible.
And for steel parts like hubs?
Steel is magnetic, so LPI doesn't work as well for subsurface flaws. You have to use magnetic particle inspection, MPI. Magnetize the part, apply iron particles, and they'll gather at any surface or near surface crack, revealing it.
What about composite blades? Different failure modes.
Composites are strong and light, but impact damage or lightning strikes can cause internal problems like debonds, layers separating, or delamination. You might not see it on the surface.
So how do you check?
The standard field method is the coin tap test. You literally tap the blade surface gently with a coin.
Listen for?
A change in sound. Good, solid bonded composite gives a clear, sharp ring. If you hear a dull, hollow thud, it indicates a void or separation underneath. That area needs further investigation or repair.
Okay, dealing with vibration. 2 key procedures: tracking and balancing. What's bleed tracking?
Tracking is about geometry. Are all the blade tips following the exact same path as the prop rotates?
How do you check that?
You set up a fixed reference point very close to the blade tip path, could be a pointer on a stand, or even just a block of wood carefully positioned. Then you slowly rotate the prop by hand, checking if each blade tip passes the reference at the exact same distance.
What's the tolerance? Pretty tight.
Extremely tight. Usually something like 1/116th of an inch maximum difference between the highest and lowest tracking blade tip. Any more than that, you've got a potential vibration source.
Then there's balancing, addressing the weight distribution, starting with static balancing.
Right. Static balance ensures the propeller's center of gravity is exactly on its axis of rotation. This is done off the aircraft.
Oh.
You mount the propeller horizontally on a special fixture called a knife edge test stand. It has very low friction pivots. Before testing, you have to make sure all the blades are set to precisely the same angle.
And if it's balanced?
It should stay perfectly still in any position you rotate it to. If one side is heavy, it will drift down. You add small balance weights inside the hub or on designated spots until it stays put. It needs to be done in a draft-free room.
But static isn't the whole picture. Dynamic balancing is done with the engine running.
Yes, and it's often the crucial final step. Dynamic balancing accounts for all the little operating vibrations and mass shifts that don't show up statically. Engine vibrations, slight assembly tolerances.
How does that work?
You attach sensors, accelerometers to the engine casing. You run the engine at a specific RPM. An electronic analyzer reads the vibration level and phase angle from the sensors.
And tells you where to put weights.
Exactly. The analyzer calculates the amount of weight needed and precisely where on the propeller spinner or bulkhead to add it to counteract the measured vibration. The goal is usually to get the vibration down to a very low level, like 0.2 inches per second, IPS or less. Makes a huge difference in cabin comfort and equipment life.
Servicing. Lubrication seems straightforward, but there are nuances.
Very important nuances. Follow the schedule strictly, typically 100 hours or 12 months, whichever comes first. But if you operate in salty air or high humidity,
At the interval?
cut it in half, usually to 6 months. Corrosion is aggressive. And here's a big one. For a new or freshly overhauled prop, you must relubricate it very early. After just the first 1 or 2 hours of operation.
Why? What happens in those first couple hours?
Centrifugal force. That initial grease packing gets flung outwards and redistributed inside the hub. This can leave voids, empty spaces where there was grease before.
And voids are bad.
Voids collect moisture. Moisture leads to internal corrosion, which you can't see. That early relube pushes fresh grease into any voids created by that initial redistribution, ensuring full protection. Critical step.
What about props that need an air charge?
Some designs use a charge of compressed gas, usually to assist in moving the blades towards high pitch or feather.
What gas should you use?
Always nitrogen. Never compressed air. Nitrogen is dry and inert. Shop air contains moisture, which causes internal corrosion.
And getting the pressure right.
Absolutely critical. You can't just guess. You must use the manufacturer's chart that relates the correct charging pressure to the ambient air temperature at the time of servicing. Temperature drastically affects gas pressure. Follow the chart precisely.
Final point on maintenance. Repair authority. What can a certified AMP mechanic actually do to a prop?
The limits are strict. An A&P can perform minor repairs only. Things like dressing out small nicks and scratches within allowable limits, painting, lubrication, basic servicing.
What constitutes a major repair?
Anything significant, straightening a bent blade, usually not allowed anyway,
Right.
welding, major material removal, anything involving disassembly and reassembly of a controllable pitch hub mechanism, or a full overhaul.
And those must be done.
Only by an FAA certificated propeller repair station holding the appropriate rating or by the original manufacturer. They have the specialized tooling, data, inspection equipment, and expertise required for that level of work. Safety demands it.
Okay, auxiliary systems. Keeping the prop working in tough conditions. Ice control. Why is ice such a big deal on a prop?
Ice is incredibly dangerous. First, it completely disrupts the airfoil shape, killing thrust and efficiency. Second, and more critical, even a small amount of ice throws the propeller massively out of balance.
Leading the vibration.
Severe, potentially destructive vibration, especially if ice sheds unevenly from one blade before the others. So you absolutely need systems to prevent or remove it. Two main types.
The older fluid type.
Fluid anti-icing uses a pump to send fluid, usually isopropyl alcohol, out to the prop hub. There's a slinger ring that spins with the prop.
And slings the fluid outwards.
Yep, centrifugal force distributes it through tubes or channels to feed shoes or boots along the leading edges of the blades. The alcohol prevents ice from sticking or melts it as it forms.
Downsize.
Weight of the system and fluid, limited duration based on how much fluid you carry. Less common now.
The modern standard is electrical de-icing.
Much more common. Uses heating elements like wires embedded in rubber de-ice boots bonded to the blade leading edges, and sometimes on the spinner too,
How does the power get to the spinning prop?
through a slip ring and brush block assembly. The slip ring is a set of conductive rings rotating with the prop hub. Stationary carbon brushes ride on these rings, transferring electrical current from the aircraft system to the boots.
Now, critically, the power isn't just turned on continuously, right? It uses a cycling unit. Why?
The timer or cycling unit is absolutely essential. It applies power intermittently, maybe 15 or 30 seconds on end, then maybe 90 seconds or more O-off-F, for a total cycle time of perhaps 2 minutes.
Why cycle it? Why not just leave the heat on?
Two vital reasons. First, cycling ensures that ice tends to shed more evenly from all blades simultaneously, minimizing imbalance during the shedding process. Second, it prevents run-back icing.
Run back.
If you left the heat on constantly, the ice would melt and the water would run back over the colder, unheated part of the blade just behind the boot.
And refreeze there.
Exactly, creating a ridge of ice further back, which can be even worse aerodynamically. Intermittent heating allows the bond between the ice and the boot to break, and the airflow then blows the ice off in chunks before it fully melts and runs back. Smart system.
Lastly, for multi-engine planes, refining speed control for noise and vibration. Basic system is synchronization.
Synchronization, or
Right.
sync. An electronic system that automatically adjusts the governor settings on each engine to make all propellers spin at the exact same RPM.
What's the benefit?
Eliminates that horrible low-frequency beat or drone sound you get when props are just slightly out of sync. Also reduces overall airframe vibration. Big comfort factor.
And the more advanced version, synchrophasing.
Synchrophasing goes one step further. It not only matches the RPMs perfectly like a synchronizer,
But it also controls the relative position of the blades.
precisely, it sets a specific angular phase relationship between the blades of one designated master propeller and all the slave propellers.
Why do that?
Cabin noise reduction. By carefully controlling when each blade tip passes the fuselage relative to the others, you can manipulate the pressure waves hitting the cabin walls. You can phase them to partially cancel each other out, significantly reducing the perceived noise level inside the aircraft. It's all about passenger and crew comfort.
Amazing technology built around managing these spinning blades.
It really is.
So wrapping this up, this look at propellers really highlights that incredible balancing act. You've got the governor constantly fighting to hold that tiny 2 to 4 degree AOA, juggling engine power, airspeed, using oil pressure against powerful springs and twisting forces. It's the complex.
And for you, the AMT, it underscores why vigilance is key. Those massive centrifugal forces mean that any flaw, a nick, corrosion imbalance, isn't just a small issue. It's a potential failure point under incredible stress. Your inspection is the safety net.
So let's leave you with a thought to chew on. Building on that idea of managing forces and materials, we're seeing more advanced composite propellers now. Composites behave differently than aluminum. Different density, different stiffness, maybe different reactions to temperature changes.
Right. Thermal expansion coefficients can vary. Stiffness is different.
Okay, so consider how finely tuned that constant speed system is. It relies on that delicate balance between CTF, ATF, oil pressure, spring tension, all based on the known properties of metal blades. What happens, or what could happen in a composite system if, say, the blade stiffness changes slightly more with temperature, or its thermal expansion subtly alters the internal clearances or twisting moments compared to what the governor expects?
That's a great question. Could it affect how accurately the governor maintains RPM? Could it influence the NTS system's sensitivity? Could it require different balancing techniques or inspection intervals?
Exactly. How might these subtle material differences challenge the existing maintenance philosophies and troubleshooting techniques developed over decades for metal props? Something to think about as these new materials become even more common.